All right, let's get ready for the final 20 minutes. I know your brains are probably fried. Mine is a little bit. We're going to get through this together, and then you can focus on assignment 4 in your article critique, okay? All right. So, now we're going to talk about factorial designs. By the end of this lecture, you'll be able to write a linear model given a factorial design, plan, conduct, interpret, and report a two-way factorial ANOVA in R, distinguish interaction effects from main effects, and suggest when to analyze which effects. Okay, so we just talked about ANOVA. We're all about controlling the family-wise error rate when we have all of these predictor variables, right? Because all of this is just linear models with categorical predictors. So you can either control the rate using some sort of correction or compare everything at once. So we avoid the jelly bean problem. So we compare all the means. Sums of squares. We were talking about how we slice these things up. And the big takeaway of ANOVA is by adding a covariate, we are able to then explain more of the variance, have a better estimate of the other effects, and reduce the error. So when we're saying that, what a lot of what we're doing right now is we're looking at the signal to noise ratio. That's what this ratio is for the F test. The signal, we're basically increasing the signal by looking at two different signals, and that helps us eliminate more of the noise, if that makes sense. Okay? Basically, we explain more of the variance by using a covariate. Well, what about, can we do this even more? Like, can we explain more of the variance? This is where factorial designs come in. So we're going to go, I'm sad about this example.
It's okay.
An anthropologist is interested in the effects of alcohol on mate selection at nightclubs. Her rationale was that alcohol had been consumed, so subjective perceptions of physical attractiveness would be more inaccurate. This is the beer goggles effect. Cool. She's also interested in how this matters for different genders, and this is going to be assuming a binary gender, so my apologies for that in this example. So, yeah, you know what? 1 minute, we're going to do this. Write in the linear model for this study. One output variable, which is attractiveness on 1 to 10, which is how much did the participants rate attractiveness, and two categorical input variables. How much alcohol was consumed? 0, 2, or 4 pints. And gender, men or women. You can explicitly write the dummy variables, or you can treat each factor like the variable in LM, the way that we've kind of done up here. Okay, 1 minute, go! All right, 20 seconds. Five, 4, 3, 2, 1. Let's come together. Okay, I need a volunteer. Who's feeling confident about their equation? Who's feeling brave? Come on, it's the end of the day. Let's get up and stretch and do fun things and be interactive. If I wait long enough, it'll be so awkward in here that someone's going to do it. I'm going to bet on it. Okay, we'll do it collectively. Look Look at me not sticking to my guns. What is the equation? What do I write first? Someone just tell me the first part of this equation from the left. Attractiveness. See, you all know it. Come on. Attractiveness. Is there a subscript? What is it? I, yes. What's next? Equal to. What's next? Beta. Is there a subscript? Sorry? 0? So beta naught, we're talking about, sorry? It's the intercept, yeah. Okay, what's next? Plus, what's next? Beta? Alcohol, okay. 2, okay. Next, we'll do the dummy variables first. Okay, what's next? Sorry, x? I. That's not quite what we want. We need to indicate that this is a variable. Yeah. X alcohol alpha 2. I. Okay, plus, I'm guessing, what next? Beta alcohol 0 or 4? 4. Because we're going to have 0 be rolled into the intercept. Okay? And then what's next? X alcohol 4I. What's next? Beta gender? Male? Okay, we'll go with male. Then female, so it would be the beta naught is going to be female, no pints of beer. Okay? Or sorry, it's going to be women, because it's men and women, slightly different. And then what do we go with, what's next? X. X, man, yeah, men. I. What next? Hey, are we done? So we got epsilon I. You knew it!
Why are we not using women?
Because women are rolled to the intercept.
So alcohol 0 and women are.
Yeah, and that's why we have to roll into the intercept, because you run out of degrees of freedom if you have 0 to 4 and men women.
Okay.
Like you end up with 2 intercepts, and it's weird. That you can't computationally calculate 2 intercepts.
But the combination of the two, right? Like
Yeah.
men 0, women 0.
Well, you just look at the means to add them. So basically, what this is saying is that this model is, you have this mean right here, and this might be, so this is a woman with 0 alcohol. And then you're going to have something like this, right? And so this might be women with 0, this might be women with 2, this might be 4, this might be men with 4, men 2, men 0, right? And so this becomes like the default, and then this becomes beta alcohol 2. Actually, this is actually average between these two. But yeah, it's like you're talking about the differences. These betas become the difference from the intercept. So the kind of generic, mathematically generic part is the women with 0 points of alcohol. Okay. This would be the way you do it if you want to do the easy mode and not type out the dummy variables. But this way we got to look at the intercept. 2 factors. It's called a two-way ANOVA. So when you get to factorial designs, you can have different factors, right? So this would be 2-way. If you have a third variable, it would be a 3-way ANOVA. 4-way would be a 4-way ANOVA, right? Etc. And specifically, this would also be known as a 2x3 ANOVA, because gender has 2 levels in this case, and alcohol has 3 levels in this case, so it's a 2x3 ANOVA. And so for one paper I'm writing right now, I'm doing a 2x3x3 ANOVA, specifically repeated measures of ANOVA, but we're not talking about blocking factors yet. So, but could the influence of alcohol change more or less depending on participants' genders? Actually, yeah, what do you think? Let's make a hypothesis. Possibly. So what this would mean that men or women might have more or less of a difference if they drink alcohol. So men might be more affected by alcohol or less affected by alcohol than women, right? So what this is asking is, can gender and alcohol consumed, do those two variables interact with each other? And so what you get is this equation here. And we are not going to write this out in dummy variable mode because you end up with a whole many tons of terms. But basically you get gender, alcohol, and then, the gender-alcohol combination. You know, is it a man that had 2 pints of alcohol? Is it a woman that had 4 pints of alcohol? That intersection of these two is here.
That might not be a linear equation.
How do you mean? Oh, but the thing is, it's sorry.
It's a combination of 2 variables combined in what manner?
Yes, but because we're just looking at means, because it's all categorical predictors, the math will work out, right? Because yeah, if it was like if it was like this is the illusion. That's why we write out dummy variables sometimes. But you kind of pretend that it's like there's different levels. When in reality there would be 5 different beta 1-2s, right? There's the intercept, and then there'd be 5 different ones of them. Okay. Okay. So we have something called a main effect, which is that is allocated to a single predictor variable. And then we have a 2-way interaction effect. And if you have a third variable, you would have multiple 2-way interactions and then 1 3-way interaction, which is the combination of gender, alcohol, and whether they come from the UK or not. I don't know. Whatever you want to do. Again, I'm using UK because the author is British in this example. So this is how it looks. Okay, the sums of squares is divided between the model and then the error variance. And you slice up the model with the effect of alcohol, the effect of gender, and the effect of the interactions. And because we use type 3 sums of squares, we know that's going to be all separated out, and the order doesn't matter, and they're going to be resilient for multiple calculations. Okay, so if we look at the data, we've got gender, alcohol, and the attractiveness that they would provide to the person that they're looking at. And we have an idea of the structure, and you know how to explore the data. So this is what we see right here. So we have we see a pretty good mix. What are we seeing from this data? Any hypotheses that we might have? Yeah, it looks like male, female. So it's actually sorry.
Females are more attractive than the males with 4 pints.
Yeah, so we see that there's not much of a difference. What we seem to see, the only difference we seem to see is at 4 pints. And there the male attractiveness ratings seem to go down, whereas the female ones stay closer to where they are otherwise, right? So this suggests to me there might be an interaction effect, because this is not all the males are lower, or all the 4 pints are here. It depends on only the male 4-pint combination is lower, right? Which means it depends on the combination of the variables, which means it depends on the interaction. So we take a look at this. Yeah, we can describe it. That's great. This is not useful. We're going to skip past this. Okay. Cool. This is a lot of nothing. This is not useful. Okay. So we might choose our contrast, right? So in this case, what we're doing is we're saying we're looking at any alcohol consumed, and then we're saying 4 pints versus 2 pints. So you can still do contrast if you want, right? So alcohol versus not, and then 4 pints versus 2 pints. And again, that's just a different way of looking at the alcohol. You could look at just all 3, right? 3 levels, 2 contrasts. That's good. Then we have male and female predictors. Contrasts are male versus female. And since you only have 2 variables, you have only 1 contrast. A second would be redundant and thus cannot be orthogonal. And that's why you have at most one value here. Okay, so we're gonna, okay, there are two ways of running an ANOVA that is factorial with an interaction effect. If you spell it out, you would say attractiveness regressed on gender plus alcohol plus gender colon alcohol. That's how you specify an interaction effect. Combines the two. The shorthand is to do gender star alcohol, which then does the cross product of all possible combinations. Okay? So this, the star notation, expands to basically be the top line. They are equivalent. Okay? And then we run our, what type do we run? Type 3, thank you. And this is the result. So what do we see? Sorry? So we don't see an effect due to gender. We do see an effect due to alcohol. But most importantly, we have an effect due to gender and alcohol combined, right? We see what we see is a interaction effect. So gender has no effect, alcohol has an effect, but the interaction effect is significant. So where do we go from here? When you see an interaction effect, it's very hard to interpret the main effects. Because we know that a certain gender-alcohol combination is different. What does it mean that alcohol is different? Is that mostly due to that interaction effect, or is it because on average they're all kind of lower? It's very difficult to tell. So when you have an interaction effect, you analyze the interaction effect first, and then you can report the main effects, but you don't really analyze them. You want to look to the real story will almost always be in the interaction effect. So what you do is you look at all the combinations. You don't look at the just the main effects. Yep.
Unrelated question.
Yep.
Why are we doing ANOVA here? Like, we did it before as well. I don't understand why. Like, what is the hypothesis that we're testing?
Yeah, the hypothesis is that for each of these predictor variables, that their beta is equal to 0. That's the null hypothesis.
So the null hypothesis would be beta is 0 for all of them and they're all equal.
Okay. Yes. Specifically, actually, in this case, we're looking at the contrast. So each contrast is equal to 0. That's the null hypothesis. And so we're testing to see if there's a difference for at least one of them, right? If we saw an effect due to gender, there's only one contrast, so it means there's a difference between men and women. If we had 3 levels, for example, if we had men, women, and non-binary, then if we had an effect in gender, we would then need to do some sort of contrast or some sort of post hoc analysis to figure out where the gender effects lie. But if there's only one predictor variable, if there's only 2 levels for a predictor variable, then you just know that they're different. But in this case, in alcohol, there's 2 contrasts. So actually, we would say that there is an effect due to those contrasts. So in this case, it does work. Yeah?
How do we determine there's an interactive effect in the scattering plot?
Well, so the way it works, I'll show you another plot that's better for it in a second. But what you see here, we put a gender as color, and we're plotting attractiveness as with along the line of alcohol. And you see down here, there's a bunch of blue dots, and there are no red dots. So that means that there are male, like this is only visible on this column and only with blue. So it depends on both male and 4 pints to be there. Whereas the female is up here, and the male with less pints is up here as well. So it's kind of outlier, and it depends on both variables. Does that make sense?
I will spend more time to do that.
Okay, let me show you another plot. So much faster without animations. But I kind of like them, actually. Great. So we test our assumptions. We have Shapiro-Wilk. Looks fine. Levine's test looks fine. Look at some residuals. They all look good. QQ. All right, everything looks good. Okay, this is the interaction plot. So what do you see here? What we see is that there are two lines that go up a little bit from female to male, which means that I guess the male participants are rating attractiveness higher. And we see that none and 2 pints are both up here. But what we see, like all three is up here, this slope is different. An interaction effect means that there's a different slope, right? So if this went up as well, there'd be no interaction effect. Okay? If these were like parallel but different, that's a main effect. Does that make sense? So if you see parallel lines, if they're far apart, that means there's a main effect, right? Or if they're like slanted quite a bit, there's another main effect. But if they cross or are not parallel, it's an interaction effect. Because that means that as you go from female to male, and as you go from, these two are the same, but this is different, as you go from these two or 4 pints, you then get a difference. Okay? Another way of looking at it, this is just flipping it from, and again, you see things cross. This is the same interaction effect seen a different way. So when you have lines that cross or that have different slopes, you have an interaction effect. We are at time. Okay, we are at 5:20 and we need to stop, and we're all exhausted. I can cover some of this next week, but some of you may choose to do an ANOVA for assignment 4. I'm guessing not many of you will. But you have the option. Does anyone want me to quickly cover the end of this? Yep? Okay. So I'm going to go. Those of you, if you want to leave, you leave very quietly. Otherwise, just hang around for like 2 or 3 minutes. I'm going to speed run it, and then the slides are all up and learn. You can self-study, and you can ask questions on CampusWire, and we'll finish them up next week. Okay? And then if you really want to do ANOVA and you need more time, you let us know. Okay? So this is the same thing, but with confidence intervals. We see that, yep, male with 4 pints is rating people as less attractive. Or noticing people who are less attractive. I don't know what the measure actually is here. Okay, so then what you do. So then we can roll out, we look at the contrasts, right? And so we see, we see the combination of things, right? So it's pretty complicated. Alcohol versus none, it does look like it's significant. I think we can trust that. It's just, with contrast, it's easier to interpret. 4 pints versus 2 pints, it looks quite a bit significant. But again, that's mostly just the males, right? In this population. So it's hard to come away with this as being significant, as being the main thing. Because what really is the big thing is probably this result. That men with 4 pints, the combination of male versus female, and then 4 pints versus 2 pints gets this, as well this, right? But I would just look at the plot. I probably wouldn't do this contrast in this case, because we see that it's only it's like 0, 2, and 4. The story really is 0, 2, and 4. So looking at the data, I would do post hoc analysis. Okay. So that's that. And then you can calculate omega squared to represent an explained variance of each variable. So that's how you do effect size reporting. There is a significant interaction effect between the amount of alcohol consumed and the gender of the person selecting a mate on the attractiveness of the mate selected. Okay, so it is selecting someone who is rated as less attractive, I guess. This indicates that male and female participants were affected differently by alcohol. Specifically, the attractiveness of partners was similar between males and females after no alcohol. The attractiveness was also similar in males and females after 2 pints. However, the attractiveness selected by males was significantly lower than those by females after 4 pints. So what this is doing is we're looking at pairwise comparisons of all 6 combinations, right? Male and female, and then 0, 2, and 4 pints. There's 6 different means that we're comparing. We compare them all probably with Tukey's, HSD, and we find that there's a significant difference with just that final one. Yeah, the textbook then explains how to analyze main effects and interaction effects. If your interaction effect is not significant, just look at the main effects. But if it is significant, look at the interaction effect and understand that story before, right? Look at the data, understand what's going on. Same message we've been preaching all term. And then there's robust tests. We're not going to cover them. Repeated measures, we're not going to cover it. That's it. Thanks so much. This was a marathon, and I will see you all next week and online in Campus Wire. Yep.